Please go ahead. Actually, before Dirk starts, I'd like to mention that there's going to be a cyber physical systems autonomy and verified machine learning event next week, next Tuesday and Wednesday from 1:30 to 5:30 British time. So many of you will be interested in that. And there's a really amazing lineup of speakers for that. So please do tune in if you can. Okay, Dirk, take it away.
Thank you very much for giving me the opportunity to talk here. I wanted to talk about SMT-based approaches to software verification. And then I thought, okay, in the time given, I can only talk about one of the SMT-based approaches. And so we have implemented all important SMT-based approaches for software verification into our verification framework, CPA Checker. And the latest addition that we had is an algorithm that is an adoption of the technique that Ken McMillan proposed at CAF 2003. And this is called, so he had a paper that was called Interpolation and SAT-based model checking. And we have revisited this with the adoption to software verification. So the take-home messages in short is software verification is a very hard thing. We have to leverage all available knowledge. And therefore, we cannot ignore McMillan's work from 2003 here. So this is interpolation-based software model checking. It is state-of-the-art for hardware. So in hardware verification, there's bounded model checking, there is PDR/IC3, and there is interpolation-based model checking. These three are the most important, I think. And so this approach popularized the interpolation and verification, and it's now available basically in so many different shapes and algorithms. This is really a very important technique now. But this very algorithm that Ken McMillan proposed in 2003 was not yet used to verify programs. And so the research questions that I have is it possible to efficiently adopt this algorithm to software? And how does it look if we compare it to the state of the art of the other algorithms in software verification, that are also based on SMT-based approaches? So this is basically everything. And now let's look at a couple of details. So I claim that this is very competitive among the software verification methods. So here's the results first, just as an overview. The blue line with the dot, do you see my mouse cursor?
Yeah.
Okay, so this is basically the quantile plot for IMC. And the others that you can see here, this is K-induction, which is not based on interpolation. The blue dashed one, the red dashed one is impact, which is another algorithm that Ken McMillan proposed 3 years later in 2006. The blue one with the diamonds is predicate abstraction, which is, I think, the oldest of the software verification approaches that was used in SLAM 2002 for the first time. And then we have also bounded model checking, and we have PDR here. So it's really the best to take the result up front. It's the best of the interpolation-based approaches that we have, surprisingly. And this was left so many years, unused. Okay, so now let's look at a little bit into more details. So we have a lot of experience with software verification algorithms from hardware. BMC was first used in hardware, K-induction, and also IC3. And now the interpolation and SAT-based model checking was proposed at CAF 2003 by Ken McMillan. And it was proposed for finite state transition systems, hardware circuits. And it computes fixed point with interpolants from unsatisfiable bounded model checking queries. And this has inspired many other approaches and had led to the invention of many more interpolation-based approaches. But this algorithm from 2003 was not yet implemented for software. Here's a little overview over all the approaches that are found in the literature. So abstraction with Craig interpolation. Craig interpolation is from the 50s, right? So it was used for transition relations, for traces, for state sets. And state sets is the most important for me here. This is IMC is the approach that I want to talk about. Impact is another approach that also Ken McMillan approached. PDR/IC3 is an important approach that also uses, can use interpolation for state sets. There's interpolation sequence-based model checking. Craig interpolation is also based for predicates and for function abstraction. So my research questions, as I said already, first, is it possible to efficiently, adopt it such that it is efficient for programs? And second, do a performance evaluation. So what is Craig interpolation? Just to remind you again, if somebody does not know it. So we have two formulas, A over state variables, like X is the current state, Y is the successor states, right? And the formula B, and the conjunction of the two formulas is ansat, and an interpolation C can be given over the variables that are used in both formulas, which means Y, the set Y here. And the interpolant has to fulfill the properties that the formula A implies C, and C in conjunction with the second formula is still ansat. If we illustrate this as state sets, and we have the original state set A here, and the state set B, which is usually the ones that should not be reached, and the interpolant over approximates the set of reached states A, such that it is easier to deal with and to compute and basically an invariant that implies our safety property. Okay, so how does interpolation-based model checking work? So we have a state transition system. We have the initial states, we have a transition, and we have the property that has to be fulfilled all the time. And what Ken McMillan proposes is we construct a bounded model checking query. This is just as usual. So it starts with the initial states. It applies the transition relation, several times, k times. And in the end, we conjunct the, that the property is not violated. And now we split this formula here and after the first transition. And we call the left part A and the right part B. And we do interpolation for these two. And we call this interpolation C1, which is a one-step over approximation of the reachable states, right? Because it's basically, it talks about the point in our state space exploration after the first transition application. And then we change the bounded model checking query such that instead of the initial condition, we use the interpolant of the previous interpolation query. And then, add the rest of the bounded model checking query. And then we interpolate again after the first transition, and we get a second interpolant, C2, which is the two-step approximation, over approximation. And we repeat this until the disjunction of all these interpolants becomes a fixed point. And then we are done, right? Then we have to see if this intersects with some bad states and so on. Okay, so now we have to adopt this to software verification. So in hardware verification, it's pretty easy. We have these transition systems very nicely represented as a monolithic loop, right? So there is some transition that is applied over all the state variables. But in the programs, we have arbitrary control flow. So control flow of a program looks much more fancy than the monolithic loop. So, but we want to have an adoption of the algorithm that minimally disrupts our program structure. And for this, we use a configurable approach. So let me just give you an overview of a summarized single loop control flow automaton here, and make us familiar, with the names that I use. So L0 and so on, these are names for control flow locations, and the fees here, these are the assumptions or statements that we find at statements in the program. So for example, we start at the initial location with the formula, with the state formula true. So we don't know anything yet about the states. And we go to the next, if we go to the next location, which is H here, I call it H because it's the head of the loop. And we, encode what happened at phi 0 in a predicate and write it down there. And this is basically our initial condition for the interpolation-based model checking. So then we are at the head of the loop and we need loop iterations, right? So we can connect the loop condition, which is true if we go into the loop, and what happens in the loop body. So we conjunct these two and have basically the transition for our interpolation-based model checking. And we can go through the loop, as often as we wish. We need only the k, k unrollings of the loop, and then we need still to check whether the property is fulfilled. So either there's some property condition inside the loop, and therefore we have this edge that goes out of the loop if this error condition is fulfilled into an error state. Or we check after the loop, when the loop condition is not fulfilled anymore, we go to some target location and there is some error condition that is satisfied, then we go to the error location. And let's encode this into our schema here. So we have either not C and phi E for the left part, or we have C, so we are still in the loop, and phi prime for the right part. And this would be our property violation, right? So now we have the ingredients, initial, transitions, property, so that we can give this to the algorithm interpolation-based model checking. So I want to use, is there a question?
There is a question here.
Yes.
Where does phi L comes from?
This is the body of the, this is an encoding of the, of what happens inside the loop body.
And are you assuming that the loop body itself is doesn't have a loop?
Yes, this is for ease of consideration is a single loop control flow automaton. And if we have several loops, like nested loops, then we have to perform a single loop transformation.
Okay.
Which basically transforms the program control flow automaton into another one that has only one loop and is otherwise behavior equivalent. So basically we have to encode, the locations of the inner loop as variables, so that we have basically reduced the one loop.
Okay, thanks.
Mm-hmm. Okay, so let's look at how can we encode this in our configurable program analysis framework, CPA checker. So CPA checker now is lots of abstract domains for program analysis. And here we are particularly interested in three. One is an abstract domain that just tracks the locations. I call it location CPA. The other one is a loop bound CPA that just counts, how many for each loop, it counts how many times have we visited the loop head already. And the second, the most important one is the predicate CPA, which we use for all our SMT-based algorithms and CPA checker. And this has, so one such abstract state of the predicate CPA has three components. It has an abstraction formula. It has the location at which we computed an abstraction last time. It has the path formula so far from the last abstraction point, and it has the it has the block encoding of the last block that we have been visiting. And since this is very complicated to remember, I bring an example and would like to illustrate this on an example with you. So first, here's a simple example program. It's an interesting example because this example is difficult to verify. You know, for example, with intervals, you cannot do anything because basically you need to discover that the invariant has to do with modulo 2. And also many predicate abstraction approaches cannot verify this. Anyway, so it's a program that initializes x with 0 and then non-deterministically in a loop increases the variable by 2, and we check, is it is it an even number still? And yes, it's an even number, and the property cannot be violated. So here is and on the right we see the control flow automaton for this. So now let us have a look at how we use the abstract interpretation framework in CPA checker to compose the formulas that we need for IMC, right? So as mentioned before, so this is a template for abstract states. We have the location, we have the predicate state, and we have the loop counter. Here we have only one loop head, we call it L4, and this gets a number and tells us how often we have already visited the loop head, right? Sorry, it counts how many times we have unrolled the loop already. Okay, so we start with our first state. Our first state is L3. The abstraction formula, since IMC does not compute state abstractions, we just leave this at top. So you can ignore this from now on. I just write it all the time so that the write-up in the framework is correct. Then the last abstraction, the last block ending is exactly here where we start, L3, and we have nothing else discovered so far. And we have not even seen a loop head so far. This is why our loop head counter is at -1. So it's still undefined, basically. Then we take our first transition to L4. And here we set the variable x to 0. How is this encoded? So the new location is L4. We didn't do any abstraction, and our the formula of the last block that we had seen is x0 equals to 0, right? So the block is very simple. It is the block from L3 to L4, and this is all encoded in this predicate, in this block predicate. And now we have seen a loop head, and now we set our loop counter to 0 because we have seen the loop head, but we have not yet unrolled. We have 0 times unrolled the loop, right? Okay, now we go to our next location, which is inside the loop. Let's assume we go inside the loop, and the location is called L5. So the next state is L5. Again, abstraction is left unchanged. We don't need it. And we remember that the last block entry was at L4. And we remember the path formula that non-det was not 0, right? Because we entered the loop, so it must have been, non-det must have returned a value that was not 0. So this R0 encodes the return value of the non-det function. And the encoding of the last block that we had is still, that x0 is 0. Block counter doesn't change. And we go to the next location from L5 to L4 again. How does this change? Abstraction does not change. Now we are again at the loop head. So we update this piece here, and we set our path formula where we accumulate what we see in the block to top, because at the loop head where the block starts, everything we saw so far in the path formula is now moved to the block formula. And the block formula is, you know, non-det was delivering not 0, and we have increased x by 2. So this is what's written and what's representing the block. And now we have visited L4, the loop head, a second time. So we now remember that we have visited the loop, that we have unrolled the loop body once, right? Good, so now we can go from, let's assume we go outside the loop to L7. So we go to L7, and now the return of the non-det was 0. And the block formula is just copied from the previous state. And let's assume we go to the error location here, because the variable is x is odd. Then we have the location is L8, and the return, you know, we copy the block formula from above. Sorry, we don't copy the block formula, but we extend the pass formula, which was the return was 0, and now we add that the variable x is odd, and this becomes our new block formula. Okay, so basically this is a very symbolic manipulation. So we get all the formulas, and now we have the ingredients that we need to apply interpolation-based model checking. So if we look at what was the first block, the initialization, that was the block that set x to 0. This is our I in IMC notation. Then we have one iteration of the loop, which was saying, you know, non-det didn't yield 0, and we increase variable x by 1. Of course, we have to encode this in the formula with SSA indices. And then we go out of the loop. The return value of non-det was 0, and we say that the variable is not even. And then we have our query, and we can ask for an interpolation. And the interpolation engine tells us x1 modulo 2 is 0. Okay, so that's the encoding. This is how it works. So we basically need our predicate analysis just to assemble all the formulas. And then we use an interpolation engine to fire the interpolation query and get the interpolants. That's all basically. So now the experiments, what do we do here? So we use CPA checker in a certain revision where we have implemented this, and we compared the results of IMC, like what I just explained, to PDR, to bounded model checking, to K-induction, to predicate abstraction, and to impact. And we use as a benchmark set all the reach safety verification tasks from the last edition of the competition on software verification. And this comprises 4,000 tasks that are not violating, that are not having a bug, that are not violating their specification. And we have 1,700, almost 1,800 tasks that have a bug that violate their specification. And the results, I split them into considering the safe tasks without bugs and for those that have bugs. Because the approach, IMC, is very good in proving correctness. This is the plot that I showed you at the beginning of the talk. So IMC is really extremely good here. And among the interpolation-based approaches, it's the best. Only K-induction is better. And all the other approaches here are way more tuned. They exist in CPA checkers since several years. And now we have implemented this IMC approach and, you know, get very good results immediately, basically. Now let's look at unsafe tasks. So tasks that have a bug. And here, as you might have expected, bound and model checking is the best, right? If there is a bug, meaning after a finite unrolling, the safety property is violated, then of course, bound and model checking is unbeatable here because it unrolls and checks for SAT and that's it. No abstraction necessary, right? And the second best is K-induction. Again, so we see K-induction is a very good trade-off. And the third one is already our interpolation-based model checking. And impact is a bit slower. So impact is the algorithm that Ken McMillan himself proposed 3 years later for verifying software. But this was based on, you know, analyzing pass by pass. Running the interpolation over single pass, and we are here using his original algorithm where the whole transition relation is applied at once for an unrolling. And the weakest here is PDR, because PDR is very time consuming and cannot solve many of the tasks. Was there a question?
Yeah, there's a question, yeah. Two questions actually. So one is that, is it the case that for the unsafe, the K-induction and IMC are just BMC with overhead?
Yes. IMC is exactly, IMC has the overhead because it does the interpolation queries. And K-induction has the overhead because it uses an engine to compute inductive invariants that are used to strengthen an induction hypothesis in order to prove the property. So yes, exactly. This is a very interesting observation. They are bound and model checking with overhead.
The second question is, how do you actually compute the interpolant? There are many ways to compute the interpolant. Are you just using, like, I think the Podlack algorithm, or
we use SMT solver for this. Our favorite SMT solver is Matsat from Trento, Italy, and this provides interpolation as a feature.
Right, yeah. Okay, so you're just relying on Matsat.
Yes. Okay, so
since you did for SAT solver, and the SAT solver is you're only using SAT solver, right? You're not using SMT.
Yes, we cannot use SAT solvers because we need to have theory support. So we have, you know, integer numbers, we have floating points, and so on.
Oh, so it is SMT. Okay.
It's SMT, yes. So here's a CPU time comparison versus PDR. So this triangle here shows where IMC, interpolation-based model checking, is faster, and the above is where PDR is faster. So there are a couple of cases where PDR is actually, you know, even 10 times as fast as this. But most of the cases are equal in runtime, or IMC is better. In comparison to K-induction, similar picture. K-induction has many cases where it is faster, but there are also many cases where IMC is faster. And in comparison with predicate abstraction, we see that the interpolation-based model checking is faster. Note that predicate abstraction also uses interpolation internally in order to come up with predicates in the predicate precision, right? Predicate abstraction needs predicates over which the abstract states formulas are built. And those are also computed with Craig interpolation. So this interpolation-based approach is better, IMC, the original one. And versus impact. So what is better, Macmillan's 2003 algorithm just adopted to software, or his later algorithm from 2006. And as you can see, the IMC is a bit better. For many cases, it has is faster. Maybe this is best illustrated really in with these quantile plots, because they have a nice, they sort the results nicely and give a better picture of the performance. Yeah, so basically this ends my presentation. So research question 1 was, is it possible to adopt efficiently the algorithm from 2003? And yes, this is achieved. We have used large block encoding for the loop bodies, and therefore we are able to encode the program control structure as a transition system. And second, this algorithm is actually now the most efficient and effective interpolation-based algorithm in our evaluation. So in conclusion, we replicated this algorithm with an adoption to software verification, and this new algorithm has a performance that is very competitive against the state-of-the-art approaches. Thank you for your attention.
Thanks.
Questions?
So Dirk, the SALI model checker combines K-induction and interpolation. So have you tried doing that?
Which model checker?
SALI.
SALI.
This is the kind of daughter of SAL.
So this combines K-induction and interpolation? Sorry, I didn't understand the question acoustically.
It combines K-induction and interpolation.
So it uses the interpolation to compute invariance to strengthen the induction hypothesis, or what does it do?
Yeah.
So we should, and your suggestion is I should compare with this tool as well. Thanks for the homework, will do.
Okay, I'm looking at the chat. There are no questions so far from the online audience. No further questions here, it seems. Supratik.
Yeah, hi there.
Hi.
Yeah, so so the benchmarks on which you evaluated IMC, is this the reach safety set, right?
Correct, yes.
So is there some kind of characteristics of this benchmark that make it difficult for IMC work? I mean, what are the cases where interpolation doesn't shine as well?
Your question is which programs are difficult for IMC and which it is good for?
Yeah, let us say compared to the other.
Yes, I cannot answer this from the top of my head. I would have to look up in the results tables. So I will take a note and send you email.
Okay. Also, I guess following up on Shankar's question, so you're using MathSat to compute the interpolants, right?
Yes.
But there could be many interpolants for the same two formulas, right? So is there something that you do to get an interpolant of the desired quality that you want, or you just take whatever MathSat returns?
For this work, we take just what MathSat gives us, and we do not try to tweak or make them better. There are approaches where you can manipulate the interpolation query such that it gives you interpolations of a certain form, but we are not doing this. We have investigated this for predicate abstraction to, investigate, can we get better interpolants so that we find the fixed point easier or so. And this was not very successful. So we couldn't achieve lots of performance gains. And in this work here, we didn't do this at all. So we just use what Madsat gives us.
Long back, there was a paper titled Beautiful Interpolants. Right?
I think this is the, if I remember correctly, the title, I think this is the technique that we tried out, where you basically, you add variables so the interpolant, right, can only talk about variables that occur in A and in B. And now you can manipulate the formulas A and B such that, you get only such interpolants that such variables in an interpolant that you really want. For example, you don't want interpolants of the form like, loop counter I equals 1 equals 2 equals 3, because this would lead to unrolling the loop. But you want to have something like, x equals y or so, if x and y are some variables that are not the loop counters, but they are manipulated in the loop. But I will.
You're saying this doesn't really help in your context, right?
Say it again.
But did you say that this doesn't really help? I mean, going and...
No, I'm saying for this work, for the interpolation-based model checking, for this algorithm, we have not tried. We use only what Madsat gives. But for our work in predicate abstraction, we have tried this once. I have to check whether I am talking about the same paper as you talk about. And I will include this in my email also.
This was also co-authored by Ken McMillan, House, Arbalguthi, and Ken McMillan. It's long back, 2013. Okay, thank you.
Thanks a lot, Dirk.
Thank you.
And